and its application in fuzzy plane fitting. These are the outline of my presentation. First, I will introduce what is my problem and what is the motivation behind that, and what is the fuzzy plane and its different forms, fuzzy plane fitting, and some applications. So these are the introduction. First, we will show how to perceive and what is a fuzzy point, and what is the fuzzy planes, and how we can perceive a fuzzy point when three fuzzy numbers on the dependent variable and corresponding dependent variable is given, and how we can fit a fuzzy plane passing through the imprecise location such that fuzzy points. So these are the motivation behind that. Suppose already we know about the conventional ideas about the classical geometries, but what about the if the size, if the data is imprecise, and how to locate an object near about any points, and how to find the distance when the data is imprecise. So this type of idea cannot be handled by conventional analytic geometry. So that's why at that point it is needed to describe what is a fuzzy space geometry. Okay. And now in the regression analysis, we know that the crisp plane give the relationship between the two independent variable and one dependent variable. But here the crisp plane is not always enough when observed data is imprecise. So and now, so there is a need to develop fuzzy planes, and it is applied to fit a fuzzy plane to the available data. And the main aim is to provide a unified foundation of framework for developing fuzzy geometric modeling, and which will be both benefit for the creative design and computer vision applications. So these are some preliminaries. These are the definition of alpha cut of a fuzzy set. For a fuzzy set, it alpha cut is denoted by this expression is the alpha cut of a fuzzy set, and a tilde t tilde 1 is the core of the fuzzy set. And this is the definition of LR type fuzzy number. A function L from R positive to closed interval 0, 1 which is non-increasing and satisfies these conditions is called reference function, and a fuzzy number is called LR type fuzzy number if there exist two reference function L and R and whose membership is defined by this expression is called LR type fuzzy number. And now what is the plane fuzzy point? A fuzzy point at a point A, B is a fuzzy set whose membership value is defined by this expression, where there should exist a point A, B whose membership value should be 1, and alpha cut is a compact and convex subset of R2 plane. And similarly, if we extend R2 space to R3 space, this plane fuzzy point corresponds to the space fuzzy point. And now we have defined a reference function of three variable. In the literature, reference function of one variable is already defined. But what about if we extend in the three variable? A function s from R3 to closed interval 0, 1, which is non-increasing along any direction emanated from the origin and is symmetric about the origin and satisfies this condition is called the reference function of the three variable. And these are the few examples. So now with the help of three variable reference function, we have defined a S-type space fuzzy point which give a unified representation of a fuzzy point. A space fuzzy point P tilde is called an S-type space fuzzy point at the point A, B, C if there exists three variable reference function and a homeomorphism with these conditions and expression is called S-type space fuzzy point. Now, this theorem shows say that any fuzzy point which is in the generalized version is an S-type fuzzy point because there always exists a reference function and a homeomorphism which always satisfies this expression, equation number 1. So, this theorem says that any fuzzy point is an S-type space fuzzy point. Okay, this is the geometrical visualization. Suppose there is a space fuzzy point whose support is like a spherical, and if suppose there is any line along the core point, there always exists a fuzzy number. So is any space fuzzy point can be visualized as a collection of fuzzy numbers. So now we have perceived a fuzzy point when two fuzzy numbers of independent variable and corresponding fuzzy number for a dependent variable is given. Suppose a tilde and b tilde and c tilde are three fuzzy numbers, then the fuzzy set defined by this expression is a space fuzzy point. And this space fuzzy point can also be seen as a S-type space fuzzy point. And this is the geometrical visualization which show that this is a cuboid shaped space fuzzy point. When A tilde and B tilde and C tilde is three fuzzy numbers corresponding to two independent variable and one dependent variable. So now what about the arithmetic operation of fuzzy points? So here to define the arithmetic operation, first we have given the idea of same and inverse points. So let P1 and P2 be two S-type space fuzzy points and consider 2 points x1, y1, z1 and x2, y2, z2 along the line L1 and L2. Then the points x1, y1, z1, x2, y2, z2 which follow their expression and with the same membership value and in the same direction is called the same points, and the inverse point which are along the opposite directions is called the inverse points. So this is the geometrical visualization where P1 and P2 are two space fuzzy points, and you can see that U1 and U2 are the same points and U1 and V2 are the inverse points. So these are the geometrical interpretation of same and inverse points. So to describe mathematically, we have given a general expression so that our computational cost can be reduced with the help of same and inverse points. So these are the general expression of same and inverse points. Okay. So now we have done with our fundamentals. So now we have defined fuzzy plane. So fuzzy plane already in conventional geometry, you know that 3 points can define a unique plane. So what about if in the place of crisp point we have given a fuzzy point? So how we can define a fuzzy plane? Let P1 and P2 P3 be three S-type space fuzzy points, then the fuzzy plane passing through that points can be defined by these membership functions, and alpha cut can be represented by a collection of planes which passing through the same points of P1 P2 and P3. So now we will move what will be the x intercept, and with the help of x intercept what will be the intercept form of the fuzzy plane. So x intercept is generally suppose there is a fuzzy plane pi tilde 3p and it intersect the x axis, then the membership value can be defined by this expression and which always will be a fuzzy number. So intercept form, suppose that a tilde and b tilde c tilde be three fuzzy numbers, and to formulate the fuzzy plane of intercept form, suppose there is 3 points p1 p2 and p3 which are at a distance a tilde b tilde and c tilde. So there will be different choices of these type of fuzzy points. So collect all the fuzzy planes passing through that points P1, P2 and P3, and in the limiting case which fuzzy plane we have found will be the intercept form of the fuzzy plane. Okay, what will be the meaning of limiting case? Limiting case, suppose that there is a fuzzy points and in limiting case theta tend to 0 and phi tend to 0, then all the collection of fuzzy numbers converges to the fuzzy number along the z axis या any y axis या फिर any z axis. So this is the definition of intercept form of the fuzzy plane. Okay. So now how we can see a fuzzy plane as a collection of fuzzy numbers. So first we see that the equation of the form, this is the fuzzy linear equation. This can also be seen as a fuzzy plane, and this equation can be seen as a collection of fuzzy numbers. These are the how we can define a fuzzy plane as a when a fuzzy linear equation is given. So, according to the reverse and plate, the equation can be seen as a fuzzy fine function from real number to any collection of fuzzy numbers, which can be represented by this expression. So, we can see that a fuzzy linear equation is a collection of fuzzy numbers where the membership function of fuzzy number z tilde can be represented by this expression. Okay, so now we can see fuzzy plane as a collection of space fuzzy point also, because in conventional geometry we see that if a plane is a collection of points. So here we can, analogous to the conventional geometry, we can see that a fuzzy plane as a collection of space fuzzy points. So similarly, in the perpendicular direction, we can get a fuzzy number, and when we take inverse of that function, we can get another fuzzy number, and we know that the product of two fuzzy number is the fuzzy point. So we can say a fuzzy plane as a collection of space fuzzy points. Now we want to fit a plane if the data is space fuzzy point. So to do the fuzzy plane fitting, we need a perpendicular distance of a space fuzzy point and a fuzzy plane, because we have just extending a total least square method, and in the total least square method we need a perpendicular distance of a S type space fuzzy point and a fuzzy plane. So okay, so what will be the fuzzy plane fitting? Suppose let us now find a fuzzy plane that fit the given fuzzy points. Suppose that there is n fuzzy points, and let p1 dash, p2 dash, pn dash be a shifted fuzzy point, which are the core plane of the fuzzy plane. And now find n fuzzy numbers along the perpendicular direction, along the perpendicular lines, which are the perpendicular to the plane ax plus by plus cz plus d. And this is the following algorithm which can evaluate the fitted fuzzy plane. This theorem shows that let n given let p1, p2 and pn be the given emphasized location. We can say S type space fuzzy point, and by algorithm 3, a fuzzy plane is being fitted to them. Then the sum d1 square, d2 square plus dn square will be the minimum amongst all possible fuzzy plane fits passing through that points. And now we have given a different interpretation of the fuzzy plane. Suppose surface fxyz is equal to 0 and gxyz is equal to 0 befit the boundary points of the support of this fuzzy number. Then the fuzzy plane is bounded by the two boundaries surface, and there must be one crisp surface between that two surfaces. Then the an equational form of fuzzy plane can be represented by equation number 3. And this equation what means? That the membership rate of a point on the fuzzy plane gradually increases from 0 to 1 as we move from surface fxyz is equal to 0 to the core plane, and decreases from 1 to 0 as we move from the core plane to the surface gxyz is equal to 0. And suppose where we can be applied these type of proposed fuzzy plane. Suppose any company CEO want to find a fuzzy function that estimates the goodness of the revenue per year based on the number of products sold per year and the number of employees working on that year. Let the goodness of revenue be represented by a fuzzy number, and from the past data we have collected these data. And now how we can predict about the future, या फिर otherwise any other time. So at that point we need a fuzzy plane. So by the algorithm from based off the given previous data, we have find this is the fuzzy plane which passes through this given data. Here we can see that in that data X and Y are the crisp point, but Z1, Z2, and Z3, Z4 are the fuzzy numbers. But in the generalized case, suppose there is another example. A city planning officials want to find a fuzzy linear function that predicts the cost of the project based on the length of the construction project and size of the construction firm. And these are the suppose previous given data. So how we can predict the cost based on these given data? So here we can need a fitted fuzzy plane so that we can forecasting about the data, and in some time application can be seen in to enhancing the image. Sometime we can see there will be also a possibility to apply this type of fuzzy plane. So these are the conclusion. I have proposed different form of the fuzzy planes and see how we can find a fuzzy point, and how to fitted the fuzzy plane passing through the given data, and what where we can see an application of the fuzzy plane. And these are the references. Thank you, everyone.
I think we have time for some short questions, maybe a short question or two. Otherwise, let me ask you a short question. I mean, so you define a fuzzy plane in terms of a family of fuzzy points, like S fuzzy points. S type, do they have to be the same type? You know, like the S type?
This type is a unified representation.
Uh-huh. It could be any type
No,
or whatever, any shape. The points could be any shape.
yeah, points could be any shape, but it will be bounded, not unbounded.
I see. Okay, thank you. So the next speaker is Tamas from Slovakia. Uh, well, I don't know if I dare to pronounce the last name. Basikal. Basikal is simple. So here we go. He's going to be talking on grid-based computing over joint possibility distribution. Go ahead. Okay, thank you.
The same department of Condenser and cooperate us popular. But what I'm going to talk about today is a little more functional. So a lot of theory there. Motivation came from the collaboration with hydrologists. They always wanted some probabilities and quantile level sets. So what how can they justify their decision when finding example dams, analyzing floods? This nice picture is on the source. There are two variables sensitivity but usually work with flood volume and uh, uh, river flow peak, so duration. So we always need to work with joint distribution probability and For this, it is quite difficult to use tools, either theoretical or practical. I mean, software tools, because every tool is good for some part of modeling problem, for it, for more precisely application of problem. So, joint probability can be constructed either as an extension or by composition of copula and marginals, and to derive the quantities and also the functions from each model theoretically or algebraically is quite challenging, and it slows down the work, the application. And also software tools, the functionality is spread about those various packages and software products. So this was my motivation to start a unifying project. Perhaps it is not a unique one, but I'm not aware of any existing. So perhaps you could give me a tip afterwards. So the first step is to have a population, something we can analyze and to use information about, or to make inference. If we have data enough, okay, that there is not much reason to model it by parametric models to make assumptions. But if we don't, we need to make some assumptions and build models, parametric models, and then either simulate new data or a lot of data to represent the population, or have either cumulative distribution function or probability distribution function to represent the distribution. And if we have one of these, we can proceed to what I divided into 3 stages. So the first one will be discretization, but first in the examples I will use a simple trivariate distribution composed by normal copula and 3 marginals of normal, exponential, and uniform distribution. You see that only first 2 variables are correlated, to make it simple. I use R as a software tool for all the calculation, and in this software or programming language, the simulation or the generating of construction of distribution, and then choosing the generating step or option looks like this, and I use Copula package, which is perhaps the most used one in this ecosystem. So the data populated looks like that. Perhaps better than having one 3D nice looking picture is to have several smaller one, but more informative you could supply by various supplemental information such as kernel density estimation of marginals. And this is the input to the first stage of my proposed approach, which is discretization. So I chose the first box. And we need breaks to divide the bins. We need midpoints to calculate density because some value needs to represent every cell. And also we will need size of each cell, which is simply a difference between breaks. Okay. And every quantity or break and midpoint could have two options of creation. I will talk about this in a while. So breaks, they are defined very transparently. Every cell is uniquely defined by its index. So in each direction, like in direction of in each dimension, x1, x2, x3 random variable, it is represented by index I, j, and k, and the ordering of the indices indicate margin of the cell. So either it is a vertex when you have only one index field, or edge or height of the cell. Fine. And breaks can be made equidistant or as quantiles for equidistant probabilities. This first case is usual with histograms, but the second one is perhaps more practical when working with Greek, just to have not much empty cells. Midpoints as well. You can have simple average, or and it can be probabilistic, like local median. Okay, I should let's move forward. There are functions to generate these breaks, center points, and differences. The naming follows the style at every function should I chose to be named as a verb, and in camel case style. Okay. So we discretized the data, and now it is time for counting frequencies and making a frequency table. In the software, it is effective to have it in a long format, not in white, which is better readable by a human, but long format format of the table is better processed by software. You know, especially the tidy approach, which I used with the ecosystem of tidyverse packages. Definition is obvious and simple, just that I follow the same notation. So I is for the first, J for the second, and K for the third dimension or random variable. This is perhaps better to show on picture what are breaks, what are center point, what are differences or sizes, and how does the frequency table looks like in the computer as a data. So this is the basic, or this is the foundation of every other step in this approach. And the fundamental function, okay, make frequency from data and specify breaks, either the probabilistic or you can use the equilistic. Usually we don't want to work with a full distribution. We like to focus on some of the random variables. So we need to marginalize the full distribution, or also marginalize the full grid. So one option is to just use this function and choose the indices which we are interested. I just reminded that it can be applied to any dimension. This is just example. So it can be 100 variables, but okay, you are then limited by your hardware, especially the size of memory. Okay. When you want, okay. There are differences between those breaks construction. So you need to be aware of pros and cons, and also marginal frequencies in two dimensions. Perhaps I will not have time to finish it. So just mention that besides marginalization, perhaps more usually we are interested in conditional distribution, and the expressions are very easy. Also, the tool to get them. Okay. And now the application. We can use this grid, either it is full or marginal or conditional, and the conditioning brings also marginalization with it. Can be used further to calculate grid of densities, of cumulative densities function, survival function, mean values. I will go through this. There is theory behind it. For example, you see cumulative distribution function two-dimensional on the right. Conditional mean, which can be used as for regression task, or you can do quantile regression. Just specifying the probability you like, and also finding level sets. Now, this method is the first one that came into my mind, and it is not perfect one. I will have to make it, perhaps make some alternative, but in the grid of higher resolution, the result is better. You can see this refined grid with resolution 100 cells in each dimension, and it is quite usable, and definitely use it. So I can share. I don't know what time do I have?
20. You don't have 5 minutes.
5 minutes. Okay, okay. So I don't need to hurry so much, but um, so if you like uh, to get a conditional density, is also possible. So because in regression, usually you give as a result a conditional mean, but what about to give the full distribution in each cut of the conditioning variable? So in this respect, you give more information, not just one value or just some variance connected with the prediction. You could give full prediction distribution, and also level sets, uh, which is used by hydrologists to uh, choose probability and find a set of quantiles. As for performance, well, yeah, you are limited whether you sample data. Uh, you cannot sample like billions and trillions of them, but they should go hand in hand with the resolution of the grid. And the frequency grid finally isn't so big, and it also depends on implementation. As I chose absolute frequencies, so you store the indices and frequency as integers, so it should be more safe. So conclusion, this is something you all already heard, which is a big pro is this it is scalable in number of variables and also in precision. So you are only limited by your computer, by hardware. It is modular. You can choose whether you want to input data or some formula for CDF, PDF. And but also there is a lot of work ahead of me. And if anybody is interested in this R software and also in this area, you are welcome to help and to be co-author of final package. Anyway, thank you for your attention, and if you want to read it, you can find my presentation.
Thank you very much. Let me ask the audience if there are any questions. Well, I always have questions, so let me ask one. So, of course, this is a frequentist approach. In your specific applications, do you find out like the form of the probability distribution, of the joint probability distribution? Like on, in the slide you showed at the beginning. So, is there, is there a specific form of a probability distribution, that you basically determine, or is, parameterized probability distribution? Do you get a parameterized joint probability distribution out of that? Yeah.
It just depends on what the distribution like to.
Yeah, I know. It's a frequentist approach, but maybe, with that frequentist approach, you can like sort of like deduce what kind of joint probability distribution you obtain. Oh yeah, this looks like whatever. So maybe you could find this out. I don't know. I mean, there must be some theory behind it, in this particular problem. So maybe people already know.
We usually take our observation fit some usually used distribution and mostly parametric and we work further. So this is what I usually do when collaborating with practitioners from hydrology
Yes.
area.
Yeah.
So I don't have much outlook.
Yeah. I don't know.
Perhaps from some Bayesian
Yeah.
point of view.
Yeah. I don't know if there's any previous knowledge. I'm not. Of course, I don't know. Yeah, and of course, you need a lot of data for your frequentist approach, right? I mean, otherwise.
Still, you can try several
Okay.
models, and then by analysis, you just choose. Okay, this model has suitable properties, for example, in upper tails, and I will use this because it corresponds to my experience with the data, with the phenomenon. So I choose the model after I fit it.
Yes.
I fit several candidates and
Yes, yeah, exactly. That's what I meant. Yeah. Okay. Thank you. Let's go on with. I think the next speaker is Jirka Gupta from Ostrava, and I guess instead of joint probability distributions, he's going to mention joint possibility distributions. So, which is related to interactive computing. Interactive computing depends on joint possibility distributions.
Thank you. Okay, my name is Jiří Kupka, and I'm going to say a few words about iterative computing. I have to say that this topic is quite new to me. It's still ongoing work. However, well, I would like to share some ideas or some problems that I had with this, but I think that there are some ideas which are of some interest, and I would like to share with them. Anyway, since I was attending fsta the first time in 2008, I always had a talk about fuzzy dynamic ecosystems. So that was my usual first slide in this conference. So I can't break this tradition, but the talk will be about something different. No, this belongs to the motivation because when we started with space and the continuous map on X, then we have a dynamical system because we can iteratively use this map and we obtain something that represents dynamics of some state. So for instance, here you can see the space X0101 and the map L, which is continuous. So this is a discrete dynamical system because you could use, I mean, for instance, some point you can map somewhere, map it again, and take the image of the image, image of the image of the image, and so on. This represents the dynamics of some initial state. And we found, so we had a crisp dynamical system, and there is a way how to define a fuzzy dynamical system, which is based on this crisp dynamical system. And we somehow studied mutual relations of this crisp and fuzzy dynamical system that is induced. And we studied, I mean, stability conditions, chaotic properties. We have several papers about size of topological entropies and some other conditions. And it came to our mind that, okay, we know quite a lot about fuzzy dynamical systems, so now it's time to move towards some applications. And there was a bit of problem. With some people, we started to discuss, okay, let's use this theory. The closest way how to use this theory is, okay, discrete dynamical systems are somehow connected with difference equations. However, when we start with difference equations, we realize that even simple difference equations are hard to compute because yeah, there are some technical duties. When we have this crisp dynamical system, the fuzzy dynamical system is obtained with the help of Zalix extension. And this Zalix extension is quite known, and many people know this. But in general, it's very difficult to obtain an approximation even of this Zalix extension. And there are some approaches for this. For example, Stepanini in 2006 defined some special form of fuzzy numbers and showed that they can be used to represent fuzzy dynamical system. But that's an exceptional paper. For instance, Schelling and Bernard Batz, they showed that, okay, we can represent the interactive computing of functions of one or more variables. However, they did just one step, and they finished with this. They also wrote a paper about interactive computing. And that was the first time I met interactivity, but I didn't know the consequences. Also, me and my student, we have a paper about some particular cases when we can take some approximations, but of fuzzy dynamical systems, but still we had some technicalities, and it was hard to extend that problem, because the problem is that not only the extension is hard to approximate, and there are a few papers about this, but also crisp dynamical systems are hard to approximate, because when you do a mistake, then the mistake is somehow spread in the following iterations. For instance, when you, an example, when you take this map, the graph of this map is this probability function, and you take this point x0. X0 is a fixed point of this map, so mathematically there is no movement. The image of x0 is x0, and when you repeat this procedure is x0 again. But when you do some computer simulation, okay, so one would expect that distribution of the forward trajectory is characteristic function of x0, but it's often not true, because x0 is an irrational number, and because of the representation of irrational number in computers, it may happen that distribution function of the forward trajectory is different, that it's near this point 0, 1, and x0. It's somehow, but that's the reason. So we wanted, so there are some, say, complications, and we wanted to start with some easier difference equations, fuzzy difference equations. For instance, those which are contain just, I mean, easy mathematical operations, additions, subtraction, multiplication, division. And even for this case, it's quite complicated to work with the extension of those operations. Usually they are defined with the help of alpha cuts. I mean, many people contributed to this, and the results are not convincing, because, for instance, when you consider the existence of the inverse element for the Zalix extension, there is none. And there are some solutions that approaches that could solve this problem. For instance, several ways of fuzzy subtractions have been defined, Hook-Ward difference, generalized Hook-Ward difference, and so on. Also, some different theories can be defined. For instance, Michal Čapek, Manči Štěpnička, they created this theory of MI algebras, and they somehow use that. And it's also possible to use the notion of interactivity. And for interactivity, it's quite powerful instrument. And in fact, in some cases, it ensures the existence of the inverse element, for instance. So we can use some subtraction with some nice conditions. When we have a subtraction, we can use fuzzy differentiability and so on. And this can be done with interactivity. And also to this approach, or this direction, many people contributed, especially active is the group in Brazil. So as me and also Peter contributed in several papers. And it's even recently, I mean, Estelle as me showed some results that seemingly provides some final solution for addition and subtraction. So the most simplest operations that we can need. However, this result has some nice some nice properties of that interactive computing. However, I mean, go through all the details, all the definitions. I mean, this is quite technical, and it was quite hard to go through. But I like the consequences. I was thinking maybe there is another representation of the results and of the outcome. Okay, so we kind of wanted to contribute to this, and we have some ideas. So I use R for real numbers, FR for fuzzy numbers. Fuzzy numbers are normal upper semi-continuous fuzzy set with compact supports. Okay, a joint possibility distribution is of n fuzzy numbers is a fuzzy relation which somehow connects all those fuzzy numbers. And fuzzy relation can be given, for instance, by a t-norm, and then we give this expression. And when this t-norm is the minimum t-norm, then we say that those fuzzy numbers a1 to an are not interactive. Otherwise, they are interactive, yeah? Or J interactive. Okay, this notion of interactivity is quite low, but in 2004, some like Carlson Mylan, they showed that there is a possibility to use it as in the definition of Zarek extension. So they define this sub-J extension principle, and sub-J extension principle is using this formula. What is interesting that if the fuzzy numbers are non-interactive, then we obtain the definition of the Zarek extension. And so they somehow show that, okay, these joint possibility distributions can be used this way, and it really works. For the inverse element, okay, we need a candidate for an inverse element. So we take a characteristic function of some inverse element. So for addition, it's characteristic function of 0. For multiplication, characteristic function of 1. As far known results, it was known for addition that, okay, we can have this joint possibility distribution such that, I mean, there is inverse element for every fuzzy set, but it's not known for multiplication. It was kind of surprising. So when we take this definition, we have this function. For instance, this could be interval I1, I2. So in the real line, and then we can have functional joint possibility distribution. And in fact, it's the joint possibility distribution which has support in the graph of the function of f. This is quite often used in some special cases when people want to use this joint possibility distribution. For instance, for those linearly correlated fuzzy numbers that have been recently used in many applications. And when we take a fuzzy set A, then we can say define a joint possibility distribution which is somehow induced by the fuzzy set A. When we take a fuzzy number and we have a map fuzzy number and we take the extension of that fuzzy number, then we can show that with respect to this joint possibility distribution, we have this interactive fuzzy numbers. This means that we can use this sub-J extension principle. And okay, The structure that we use is, we will say, a topological group. Topological group is a group for which the group operation and its inverse are continuous. And the continuity, of course, is the topological space B times G, that's the group product topology. And we use this group G, which is in the real line. So we take we call it natural topological group. And for this, we have, say, this statement that you take this natural topological group, then for every element, we can find, say, a fuzzy number such that with respect to this joint possibility distribution, we find an inverse element. So this fuzzy set B is the inverse element of fuzzy set A. Okay, so this somehow, I mean, confirms the result for the addition, but somehow extends the result for the multiplication. Of course, I mean, some more results can be defined, for instance, of this form. But what is most important is that the diagonals. It seems that the diagonals can be important in this computing because when we had in this, we obtain something that is defined on the side diagonal. For fuzzy numbers, we can define the main diagonal, which is you just in the plane you take the left points of alpha cuts or the right point of alpha cuts, and you get the main diagonal, or you can combine the right left and the left right points of those positive numbers in order to get the side diagonal. And it was shown that by Korean and Fuller that in a dimensional case there is a necessary a sufficient condition such that when we check for the equality of interactive and non-interactive computing, and it was done exactly on the main diagonal. So there was some condition for functions of n variables, such that the function had to be strictly increasing at each variable. And for this case, there was some condition for the main diagonal, for which there was a if and only if condition for which interactive and non-interactive computing somehow agreed. So we just took a bifunctional joint possibility distribution that we took that just the possibility distribution that is defined only on diagonals. This case, we consider the strictly monotone continuous fuzzy numbers. I mean that we take fuzzy numbers which are continuous but don't have pieces of monotonicity. So we take a joint possibility distribution of those two numbers. In fact, the joint possibility support of the joint possibility distribution is on the diagonals, and those one-dimensional maps just define the values of this joint possibility distribution. With this, we obtain some representation of joint possibility distributions, and we can play a bit. It's I will mention some data developed by Estelle Esme, because what they did, they showed the constructed parameterized family of J gamma of joint possibility distributions, such that they, with the help of this parameterized family, they computed this interactive they define interactive addition and subtraction with some nice properties. For instance, they could guarantee the inverse element, the parameter gamma, was defined in order to control how narrow the outcome is. And so this way they somehow show that they could control the Hausdorff norm of this fuzzy number. And these operations also generalize this known more general definitions of fuzzy subtraction. And we can show that, for instance, in cases like this, we can use this B-functional joint possibility distribution in order to get the same results. So for every gamma, for every two fuzzy numbers, we can have this. So the approach can be represented by by this joint possibility distribution, which is dependent only on diagonals. Similarly, also for subtraction or maybe for some other maps. So this way we obtain, say, some properties that are consequences of the results of the paper, which was of consequences which appeared in the paper by Estero Esme. And all, however, we have a better insight how this interactive computing can work with this. So ongoing, it seems that this B-functional possibility distribution can help to understand how, for some operations, how this interactive computing works, and can simplify some computing more general functions, for instance, that preserve the monopoly in each argument. And those operations need not be only addition, multiplication, subtraction, division, but also maybe some other one. Okay, so, but maybe next time more words.
Okay. Thank you very much. Oh, actually, we shouldn't be asking any question, but somebody. Yeah.
Yes.
Yes.
Okay, so the first question is, are you stick to triangle numbers or not? Are you the triangle numbers, triangular shaped?
No.
No.
Not.
Okay, it's good. Yeah. The first is, I see here non topological groups, but probably linear topological spaces. In my opinion, yeah, they are better suited, yeah, to the purpose, yeah, of this investigation.
It is done already in this paper in 2000. This paper proved
Yeah.
this condition. They also work with linearly correlated fuzzy numbers. They did it for functions of more dimensions. In fact, they considered triangle fuzzy numbers, and also the string possibility distribution was characteristic function of some on some real line. So that was kind of way that solved this.
Yes, yeah, and so yeah, and if you leave this space of triangular shaped numbers, yeah, which I really strongly recommend, and you work with say bell shaped functions, yeah, which is wide version, yeah, of this, you can probably work with using theory of generalized functions. Actually, generalized functions, yeah, is a well-known field, yeah, that is specially elaborated for working with extensions of points like so-called distributions, yeah, and there are plenty of results how really things can be performed there, yeah. They are based probably also on inner spaces, yeah, but when you start, yeah, looking in this direction, you will see plenty of really options, and it seems to me that it will help you significantly, especially, yeah, solving this type of equations. Thank you.
Thank you very much. So let's go on to the last speaker. Yes. Sorry for the slight delay. Again, now the last name is even more difficult. So. Susanna is just fine. So the next speaker will be Susanna. Okay. But if you want to say your last name also, you're welcome.
Okay, thank you for the introduction. So I'm Zuzana Ondukowiczowa. I know it's quite a Pardon me, so Zuzana is okay. And for today's presentation, I would like to present to you something about the entropy, a particularly differential or continuous entropy, and I would like to generalize the concept from the original additive case to fuzzy measures and other fuzzy concepts necessary for this. So let me start with the additive approach. Here, throughout the whole presentation, I would need to assume that we have a measurable space, so non-empty sample space, and some sigma algebra, where we assume a probability measure, so additive measure which has a normalization condition, and a random variable or measurable function. And the basic idea or the basic concept in a probability is the cumulative distribution function. It aggregates the information about the probability measure and the random variable in this formula here. And if this cumulative distribution function is absolutely continuous, then we can say that it has a probability density function and it is connected via integral or derivative. However, from these formulas, we cannot see how the probability distribution function is connected with the probability measure. And for that, we need the derivative. To be exact, we need the random-Nikodym derivative, which shows us the relation I mentioned. So the relation between the probability measure and the probability density function. Here we need to assume some more conditions. So okay, in the numerator, there's a probability measure, and in the denominator, there's a Lebesgue measure, which is somehow like a reference measure here. And these two need to be sigma finite, and there should be some other condition, meaning that if every time this lambda is equal to 0 for any measure, then also this probability measure should be 0. Okay, and with these, you probably know the entropy formula in this form. So with the probability density function and replacing this PDF with the Radon-Nikodym derivative, we can obtain this formula for the entropy still in the additive case, where lambda is taken here as a reference measure. What needs to be said there is that this reference measure does not affect the result, meaning that taking any other reference measure gives us still the same entropy value. Still, the final entropy value is the same. If we also use the property that we can somehow cross out these lambdas here, so we can change the integral measure to probability measure, we obtain this a bit shorter formula. So in the additive case, in the additive approach, we have these two entropy formulas. And with them, I would like to make some kind of a generalization. However, at first, let me explain to you why am I doing this. So my basic idea is that, okay, entropy is a well-known concept, famous for many, many years. It originated in thermodynamics. It is somehow connected with the unorderedness or messiness in a system, the closed system. So, for example, it can be taken as a measure of messiness in a way that it can be connected with the amount of energy we need to untangle this knot, for example. It can also, from the second law of thermodynamics, can be seen as an arrow of time, because as you probably all know, the entropy in the closed system is still increasing. So if we have two different states of one system, and we compute the entropy value and compare it, we can say which one is the first and which is the consequent one, second one. Much later, Claude Shannon, in his mathematical information theory, used the concept of entropy as the measure of uncertainty in communication. So, for example, when we have some kind of a communication channel, here it's the, let's say, telephone, and the uncertainty here is connected with uncertainty of received message. So the received message doesn't need to be the same as the original one because of some bias throughout the communication channel, or for example, some noise. And there is And that's why the entropy is so interesting, because it can measure the uncertainty in the obtained message here. However, what I was mostly interested in is the principle of maximum entropy postulated by James here. And it states that if we want to describe closed system, we need to find the proper distribution function for that. And the distribution should be should satisfy all the constraints, or should have all the properties we want to have, because as we know about this system, however, we want to be unbiased and doesn't add anything additional to this system. So when I was thinking about it, it's something like a prisoner with a chain, with his with a metal ball chained to his ankle. So he can move, however, he has some constraints where he can go, where he can move. Okay, and with this principle of maximal entropy more mathematically, we get some constraints here. So the first one is a normalization constraint, which is quite normal in the additive approach. And the second constraint or type of constraint is it can be any other constraint where r is the function of x, and along alpha here is some constant. So we use the Lagrangian, which is this formula here. So this is the entropy. This is the normalization condition multiplied by some constant. And here are all other constraints, again multiplied by the constant. This method is in fact called the method of Lagrangian multiplicator. So quite familiar, probably famous maybe more in physics. But okay, and as a result, we want to maximize this formula and obtain the proper distribution function describing the closed system. So for example, if we only have normalization condition, we get uniform distribution. So for example, when spinning a roulette, we don't know which number will be the best to choose, but all of them have the same probability to appear. If we know not only normalization condition, but also expected value, mean, then we get exponential distribution. And if we also have additional information about the standard deviation, we get a normal distribution. So for example, it can model weights of newborn babies, for example. Okay, and this concept, or at least I was thinking that this concept would be very, very interesting to generalize into the fuzzy setup. So how would the distribution functions look like when we use not probability measures, but fuzzy measures? This was my idea. However, it was, um, as I thought about it more and more, it's quite far-fetched idea, and a lot of work will need to be done in order to get to something like this. But I would like to present to you my first steps in this problem. And the very first step, and maybe the most important, is properly defining the entropy for the fuzzy case or for fuzzy measures. So I will need to take additive measures and generalize them to fuzzy measures. So easing the additivity condition to monotonicity. That means that we will need to change the original Lebesgue integral to Choquet integral. And since the entropy has a logarithm in the formula, we need not only Choquet integral for non-negative functions, but extended Choquet integral, so asymmetric and symmetric Choquet integrals. Maybe just a quick note. So the original Choquet integral uses survival function, which is somehow complementary distribution function to the cumulative distribution function I mentioned at the beginning with the fuzzy approach. So maybe more proper or better generalization for this concept would be using not this Choquet integral here, but some complementary Choquet integral. I'm just mentioning it because we had an article about this complementary Choquet integral, and it would be maybe very interesting to look at the direct generalization. But since this community is basically working with this formula for presentation, I chose this one. Okay, so we have a Choquet integral, and then And then we also need to look at the Radon-Nikodym derivatives and generalize them into the fuzzy setup. So we took the formula for the derivatives and only changed it with the Choquet integral here. However, these derivatives are not so easy as in the additive case, and it is quite simply seen only with the existence conditions. They does not exist only when assuming this sigma finiteness of both measures and some absolute continuity between them, but we need to assume at least submodularity of them according to Huber-Strasse, or if we want to ease the condition of submodularity, there's subadditivity as given by graph. However, we need to add a strong decomposition property, which is, I think, derived from the hand decomposition of measures. Okay, since we want to use these derivatives, we also look at the computational algebra. So here are some basic properties of them. What can be very interesting, as I mentioned, this complementary approach. Then we also looked at the connection between the derivatives with respect to the original measure and the dual measure. And we saw that they do not coincide, but if we take subadditive or superadditive measures, we can compare them, so there are inequalities. And what would be very important for the next slide is this condition or this property. We want to we can change the integration measure, so something like crossing out this mu here, but it holds only when we got the non-negative function or random variable here. For generalization, so to the extended integrals, it holds only for the symmetric Choquet integral. Okay, and for some computations, it would be great to have some kind of a formulas for computing not only the integral itself, but also the derivatives. And the biggest work was done by Professor Sugeno here. However, he got very restrictive setup, so he only assumed the real line as the sample space of intervals beginning with 0 and only Lebesgue measures. So it would be great to, again, use not so restrictive setup, at least with any real interval and also with the distorted probabilities. So this is my task for these days. I'm working on it right now. Okay, so now we have everything we need for proper postulating the formulas for the fuzzy entropy. So with these originally additive, we just replace the measures to fuzzy measures, Radon-Nikodym derivatives to Choquet Radon-Nikodym derivatives, and the Lebesgue measure to and the Lebesgue integral to Choquet integral or extended Choquet integrals, and we get these two formulas. The first one is quite clear, and the second one with the symmetric Choquet integrals is derived with the property I mentioned on the previous slide. So we can change the measure in the integration. Okay, so these two formulas are like a proper definition for entropy in the continuous case of differential entropy with fuzzy measures. And now just briefly about like properties about it. So as I mentioned, I'm interested with the duality or dual approach to this. So I was looking at the properties where I can compare the entropy, where the reference measure is original or dual measure. So there are some inequalities depending on if the measure is sub or super additive. There's also some positive homogeneity. First, with respect to the reference measure, where this formula is overhauled in the additive case. If we don't want to add any other like additional properties, we only got the inequalities here for both extended Choquet integrals. And if we assume, moreover, something like a submodularity or supermodularity of the reference measure, we can get something very, very similar in the formula. However, there is only an inequality here. And we need to only assume a symmetric Choquet integral. It does not hold for the symmetric one. The same with very, very simple very, very similar results can be done also with the input measure. And my last remark would be the relation or connection between famous Kullback-Leibler divergence, which is used in many, many applications. And we postulated in our previous article, we postulated again, proper formulas, proper definitions for this Kullback-Leibler divergence. And just comparing the formulas, we can see that this Kullback-Leibler divergence, only when taking the second measure as a reference measure, of course, with a minus sign, we can get the entropy formulas I presented earlier. So there is a strong connection or strong relation between them, and it could help not only with the properties, but also with some applications in the future. So all from me, and thank you for attention.
Thank you very much, Susanna, for your very nice talk. I guess we don't have any other talk, so go ahead with your questions. Anybody has any question? Yeah.
We have opposite inequalities, yeah. So the same parameters on the left and on the right, they will go y actually, and also the previous slide was similar.
Yeah. In these two, it depends on the value of this parameter or this constant k. Because if there's a logarithm of k, and logarithm, if it's in the interval of 1 to 0, the logarithm is negative. And as can be seen in somewhere here, okay, here, for negative part of the function, you need to assume a dual measure in the case of the asymmetric shock of the integral.
Understand what bar means.
Yes. This is the dual measure. So when we need to use the dual measure, the inequality sign will change. So this is why there are different inequality here. There are different inequality signs when taking k in the interval 0, 1 and bigger than 1.
Thank you.
Thank you.
Let me ask you, what is the derivative in your case? So I don't know if you explained that. This different derivative symbols. What do they mean?
That we, in case of Lebesgue measures, even here, we, as a derivative, we consider this function f here. So we are taking like an inverse problem to computing the integral itself. So we are trying to find this integrated function when we know the integration measure and the result. So this is the same idea with shock integral. So we want to compute this g function as the input or as the argument in the integration.
Mm-hmm.
However, since we are doing it in a fuzzy case, it's not so easy as the derivatives in the additive case, and that's why I presented all the properties and necessary conditions for existence and so on.
Okay, thank you very much. Yeah, I don't know. Yeah.
No, it's not always possible. These two conditions of existence are only one-sided conditions, so we don't have like a characterization when the derivatives exist or not, if I'm not wrong.
Okay, thank you. So that's all for now. So now we have time for lunch, and so let's close the session. End the session. Thank you.